Hola guys, welcome to my channel. So today we are going to answer the nuclear physics question. So this question is taken from the last semester final exam 2022-2023 session. Without further ado, let's get started with question 1a. Calculate the rest mass energy in mega electron volt. Given 1 AMU is 1.67 times 10 to the minus 20 negative 24 gram. Is it the same as the atomic mass in periodic table? So let's try to find the value. So first, we can use E equals to mc square formula, and then we substitute the value of m and c squares. So the SI unit for mass is kilogram. So we change this given 1 AMU into in kilogram units. So which is 1.67 times 10 to the minus 27 kilogram, and then we multiply with the c square, which is speed of light square, 3 times 10 to the 8 square. We will get 1.503 times 10 to the minus 10 joule, and then from this joule we need to change or convert it into electron volts. So we need to divide the whole thing by 1.602 times 10 to the minus 19 will result into electron volt unit. So you need to know that this value 1.602 times 10 to the minus 19 is the elementary charge, okay, the value of electron charge basically. So upon simplifying the value, you will eventually get that the result will be 938 mega electron volt. Okay, so is it the same as the atomic mass in periodic table? So the answer is yes. Is it the same? It is the same. Why? Because 1 AMU is basically defined as the mass of the 1/12 of the carbon 12. So the mass of the 1/12 of the carbon 12 is basically exactly the same as this value. So in conclusion, the rest mass of 1 AMU particle is equivalent to this value, okay, 938 mega electron volt. Alright, question B. Moving on. A weak interaction of range 10 to the minus 18 meter. So this is range R 10 minus 18 meter. Find the allowed mass of the interacting particle. So this is the Heisenberg uncertainty principle formula. So we are given. So it's basically we need to find what is the maximum allowed mass such that the weak interaction existed at the range of 10 to the minus 18 meter. So this is a very weak interaction force, which is referring to, for example, the nuclear force. Okay, so nuclear force has a very limited and a weak interaction range force. Okay, but it is the strongest one, yet the range of the interaction is very limited or very small. So compared to the electromagnetism force or electric force or magnetic force, so electromagnetic force basically, compared to electromagnetic force, the range is from negative infinity to positive infinity. So the range is infinite or infinity range, but it is not as stronger as the nuclear force. Okay. So we are going to find what is the allowed mass for this weak interaction force. So we are given the Heisenberg uncertainty principle, which is delta E, delta T greater more or equal to h bar over 2. Okay, but we know also that E is equals to mc square, so we can put delta E equals to mc square, and we know that also the speed of light is equivalent to range divided by delta t. So this is actually from the distance formula. So velocity is equals to distance divided by time, so it's similar, but this is in terms of light. Okay, light. So speed of light is the range divided by time taken. So we can substitute these two equations into the Heisenberg uncertainty principle. So E is mc square, so I will substitute mc square. Delta T is basically R divided by C. Okay, so R is basically h bar over 2, so this and that cancels, mc, like that. So h bar is basically h divided by 2 pi multiplied with 1 over 2 mc. So R is h is 6.63 times 10 minus 34 joule second divided by 2 pi 1 over m. So the given m, we need to find the allowed mass, so we need to make m as the subject, not r. So m as the subject. So m as the subject, which means m here, r supposed to be there. R. So r is what value? So 2 times r is 10 to the minus 18. C is 3 times 10 to the 8, is it? Meter per second square, meter per second. And then we need to evaluate this. And don't forget to divide by electron charge or elementary charge, which is 1.602 times 10 to the minus 19. Okay, 1.602 times 10 to the minus 19. Why? Because I want to change this h bar formula, h bar unit from joule to electron volt. Okay, so that's the standard unit for the allowed mass in the nuclear physics course. Okay, so we need to convert the joule into electron volt, so that's the reason why we divide by elementary charge. So let's evaluate that the formula. So I get about 1.0977, maybe 1.0 0.98 times 10 minus 6. So this is in the unit of electron volt time second square over meter square. Okay, so because looking at the unit, so this is actually the unit of 1 over v square. So I can multiply it with c square, so that the unit will becomes EV over c square, like that. Okay, so it is just the matter of transforming or converting the unit into the proper one. But if you want to leave the answer like this, then go ahead. It is also considered as a correct answer, but I want to simplify this. Okay, so I multiply with c square. So c square is basically 3 times 10 to the 8 square. Okay, so I will get about 98 giga electron volt over c square. Okay, so that's the answer. So this is the value of m. So for the last question is to calculate, so we already done a, b and b. So then c, calculate the radius of the nucleus of mass m equals to 64 using the relation. So this is the formula given, with r naught is 1.2 femtometer, given experimentally measured radius is 4.98 femtometer. Find which value of r naught fits the experimental data. So this is easy. So c, r equals to r naught a to the power of 1/3. Okay, so we know given the atomic mass A is 64, right? So this is not m because m is mass, but atomic the mass here is referring to atomic mass unit. So it's the unit, the what we call the variable is atomic mass unit is given by A. Okay, so A is 64, so we subs in the value. So given r naught is 1.2 femtometer, so r will be 1.2 femtometer times 64 to the power of 1/3. So 1.2 times 64 to the power of 1/3 is 4, if I'm not mistaken. Is it 4? Yes, is it 4? That's 4. So 4 times 1.2 is 4.8. Okay, but it is mentioned here that the experimental data of the radius is 4.98 femtometer. So 4.998, right? 98. So we want to find the appropriate r naught value. So we just sub in back. So r experimental is 4.98. So r naught times with a. So a is 64 to the power of 1/3. So r naught is 64 to the power of 1/3 is 4 divided by 4.98 femtometer. Okay, so we evaluate the value. 4.98 will be resulting in 0.803 femtometer. Okay, so wait, Am I correct? Wait, I think there is a mistake here. This is supposed to be 4.98 divided by 4. Okay, not the other way around. So it's 1. So this is mistake. 1.245 femtometer. So this is the most appropriate value for R naught. Okay, so that it fits the experimental data. Okay, so yeah, I think that's all for the question 1. So in the next part of the video, I will attempt to do the next question. Okay, and that's all for now. Thank you.